The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, good evening, folks. Welcome back to another great episode of our Best Practices webinar series with Sevensignal. I see a lot of you have already tuned in early, so please, if you want to, let us know where you're logging in from, what part of the world you're joining us from, if you are in the office today, if you're working from home. I am back in the Cleveland headquarters office today, and we are joined by Gjermund, who is joining us from Norway. Thank you so much for being here, Gjermund.
Hello.
And we are also joined yet again by Jim Vada, who is also across the office from me in our Cleveland headquarters. Welcome back, Jim.
Good to be back in beautiful Cleveland.
On a beautiful, rainy, cold day.
Just like yesterday. Does it ever change here, or is it always like this?
It can surprise you sometimes. Awesome. Well, we have a great show here today. I see a lot of you dropping in the chat where you're joining us from. We have Keith joining us from Louisville in the office. We have Lex joining us from Dallas, Texas. We have Harry joining us from the Netherlands, working from home. Thank you so much for joining us today. We have Wayne in the office in Denver, and I see a few more of you dropping in where you're joining us from. We'll go ahead and circle back to that. So thank you so much for being here, and we will go ahead and get started today. So we are Sevensignal, the leader in wireless experience monitoring, and we'll go a little bit more into depth as to what that means and who we are as Sevensignal with our mission. We have a great topic here today and a very special guest, as I mentioned before, Gjermund, joining us from Norway. Thank you so much again. We have a great topic, as I said, airtime duration for 802.11ax compared to 802.11ac. Really excited to dive into this. As I mentioned before, we have Jim Vada and Gjermund joining us, and I am Kelsey Rizzuto, the marketing specialist for Sevensignal. And we'll go ahead and get started here. A few announcements before we jump into the presentation today. For those of you who have joined us in the past, these will sound familiar, but we'll just run through them again. We do partner with CWNP for every single one of our webinars. So by watching these Wednesday webinars, you are eligible for CE credits. If you're pursuing a certification, just send us a message or drop a comment in the chat here, and we can send you over a certificate per request. We also host a product tour every single Friday at 12 noon Eastern at that link, go.sevensignal.com/tour, and we'll go ahead and drop that link in the chat as well if you care to register. We don't go too deep into the product here on these Wednesday webinars. Those are what our Friday product tours are for. But I will go ahead and read off just a few exciting announcements here with some product updates. We announced a few weeks ago our release of Mobileye for iGel Linux. Additionally, we recently added enhancements to the Sapphire over-the-air mode. And this past month, we announced the release of a portable Sapphire sensor. So if you haven't joined us recently for a product tour, a lot of exciting updates there. So if you want to go ahead and register, we will drop that link in here. Moving forward, we do post all of our archived webinars to our YouTube channel. So you can go ahead and watch and rewatch some of your favorites from the past. And we will post today's broadcast on there as well later this afternoon. Additionally, we are very, very active on our Twitter account, and we post our slides for each presentation a few hours after the webinar. So if you follow us on Twitter, you can find those there. If you're not active on Twitter and still want access to those slides, that's no problem at all. We can email those to you per request as well. Another reason to follow us on Twitter is that we give away a lot of Sevensignal merchandise to those who are followers of us and to those who engage with our trivia questions. So we have 3 very lucky winners from last week that I'm going to go ahead and read off. We had Ego Ejero, Paul Castro, and Rochelle Streber. So thank you to you 3. You should be receiving some very special Sevensignal merchandise in the mail soon. And to the rest of you on the line, go ahead and engage with our trivia question today and give us a follow, and we'll go ahead and move forward here. One last announcement before we move forward. Again, if you've joined us in the past, this may sound familiar, but we have recently been recognized in the Gartner 2020 Market Guide for Digital Experience Monitoring. Sevensignal has been recognized as a representative vendor for Mobileye. Really excited, really proud about this. So we'll go ahead and drop a link in the chat here as well to access that report if you're interested in learning more. All right, on with the show here. So just a little background on Sevensignal and our history. We were established in 2007 in Helsinki, Finland, and we are now located, as I mentioned before, in Cleveland, Ohio. We're really proud of the 1 billion data points that we're analyzing daily, in addition to the 5 million devices we're monitoring daily as well. We have over 200 customers, over 30 partners, and 14 patents. So that essentially goes to show that the technology you see from Sevensignal, you are only going to see from Sevensignal. Additionally, we are certified in over 40 countries, and we're GDPR compliant for our EU folks on the line here today, which essentially means that we take data and privacy very, very seriously for all of our users across the globe. As I mentioned before, we are Sevensignal, the leader in wireless experience monitoring, and we're here because the digital experience matters, and it's largely related to Wi-Fi connectivity. Usually when you're encountering some sort of Wi-Fi issue, it bubbles up to one of these top 7 Wi-Fi problems: congestion, coverage loss, co-channel and radio interference, etc. And how we're able to detect those is we give full visibility into the end user experience through an outside-in approach with Mobileye and Sapphire. We are also completely AP and device agnostic, which means that the great tools, great technologies you already have installed on the network, we're incredibly complementary with as well. So as I said, we are able to detect these top 7 Wi-Fi problems by living on the edge of the network, running active and passive tests, looking for things like packet loss, latency and jitter, adapter or driver issues, and more. So to go further into what makes us so different, if you look at your typical enterprise LAN infrastructure, you've got great tools, great technologies on the network, like your Riverbed, Cisco, Aruba, Appneta, etc. But what Sevensignal does is pick up where they leave off, taking it one step further. With Mobileye, this can be installed on essentially any mobile device, from your laptops, your mobile phones, your Zebra scanners, workstation on wheels, and more. And it can be installed on any macOS, Linux, Android, or Windows device as well, giving you full visibility into the network, living on the edge, so you know exactly what's going on in that wireless network environment. Additionally, we do provide Sapphire, which are our sensors installed up in the rafters, looking down on the network for that service level quality and RF visibility, giving you that full perspective. What we can do further also is giving you that external network visibility. A lot of you on the line today, as I saw, are working from home. So with Mobileye, we can give you that perspective into those external home networks, whether you're in an apartment building, at your house, working from a coffee shop remotely, and more. And as I've said and have said many times before on these webinars, work from home is here to stay, and we're living that reality every single day now. And being at home and staying connected, it's not just nice to have a good Wi-Fi connection, it's mission critical. So we want to be able to give you that visibility and that connectivity to ensure that great digital experience, no matter where you're working from. So with that, we have been doing a give back. Mobileye offer 50 devices for 50 days in the midst of this external home network and work from home reality. And we'll go ahead and drop that link in the chat here as well, so you can go ahead and check out what there is to offer. All right, as I mentioned before, we do trivia questions every single webinar. So I'm going to go ahead and launch a poll that Gjermund provided for us, and we will see how the audience does here. Are you all able to see this question here?
Yep, we can see it.
Awesome. So when we are changing from single user to multi-user OFDMA transmission and going from higher data rates to lower data rates, will the throughput of each client/station increase, decrease, or it depends?
Lot to think about with this one. Interesting to see what our audience says.
All right, I see a few of you still dropping in your answers here. And I'll give it a few more seconds before I go ahead and close this poll now. All right, how did our audience do today?
Well, in my mind, you know, it depends is almost a universal answer to a Wi-Fi question. What do you think, Gjermund?
I think actually every alternative is correct. It's both increase, decrease, and most likely it depends. So it's have the best answer, best of the correct answers.
All right, great job to you all.
Yeah, and hopefully some of the things you'll share today, Gjermund, will help explain why that is the right answer.
Yeah, I have to try.
All right, awesome. Thank you all. I'm going to go ahead and pass the controls here over to Gjermund, our special guest today, to give us a little introduction and go on with his great presentation today.
Okay, let's have to.
Oh, looks like the window's cut off a little bit again.
Now I'm back
There
to
we go.
normal. Yeah.
Yep, perfect.
I have learned. Okay, my name is Gjermund Raaen. I come from Norway and will today speak about the airtime consumption for 802.11ax downlink OFDMA TXOPs and compare them to AC TXOPs. So we look at the full TXOP. So, and we will use my airtime calculator to visualize those durations. And we will use the result to see the effects on when we are sending data down to some clients. And maybe see where AX could be better than AC. So, as I say, my name is Gjermund. I have a Twitter handle, Gjermund Raaen, and I also have an own website where I have the last year written a lot of blogs on OFDMA and Wi-Fi 6. I have a lot of certification in the CWNP program, and also ECC design and some Cisco certification from 4 to 5 years ago. I don't work with Wi-Fi at my daytime work, but because of my knowledge, I get some tasks sometimes, and I also do some courses and information to my colleagues. But the thing I will tell you about today is more like a hobby and passion, not my daily work. I'm also new in the Wi-Fi community. I discovered Wi-Fi as a technology only 4 years ago, and it hit me, and I think about Wi-Fi almost 24/7. You can see some pictures from my region. The two to the left is from my veranda. The upper one is on a beautiful summer day, and the lower one with the small sun is from approximately January 25th. It's when the sun came back to Bjørkvik after being away for almost 2 years. That day is a party in my town. And during this time, we have a lot of polar lights at the skies. Pretty amazing. Bjørkvik is way north in Norway. If you compare it to Canada, we are up in the Fox Basin, north of the Hudson Bay. But because of the Gulf Stream flowing hot water from the Caribbean Ocean to the northern Europe, it's quite nice to live here. But let's go into business. I developed a Wi-Fi AirTime calculator 1 year ago. It calculates the duration for a full TXOP or transmit opportunity in a 5 GHz band. And it's different on all the available files in the 5 GHz band. both OFDMA, OFDM, or 802.11a, 802.11n, AC, and also downlink OFDMA for in 11AX or HE. I will change between OFDMA on VHD or ACAX during the full webinar, so just bear with me if I use different words. My airtime calculator also calculates the diffs or IFS in the start of the TXP and the contention window, which means it's calculate the duration of the waiting time or the CCA. We will look at it later. And you can find it on the link in the bottom of the page, also from the front page of my blog. What does a TXP look like? This is a standard TXP with a lot of small pieces. It always starts with a diffs or IEFS if it is a QoS frame. Then is a contention window. The two first is what we also call dead time or waiting time. Then we often send a request to send, consisting of a legacy preamble or the physical header and the frame body. So then some waiting, a clear to send back, consisting of a legacy preamble or the physical header and the frame body. And then we are sending the QoS data or the data frame. Also with legacy preamble, we have physical header for the file we are using for the data. This change between HD, VHD, or HE, or between 11N, AC, and AX. The blue field is different from the different files. Then the data, and at last, we have a block acknowledge or acknowledge process. And the only part who's actually sending user data is the green one. For those who have looked at Kit Parsons' presentation the last month, he have also showed this TXP either by using my calculator or the one from Aruba. If you go into the calculator, it's an Excel spreadsheet. We have 4 scenarios, 2 first for non-HD, 11A, N, and AC, and the 2 last one for downlink OFDMA. And in all the yellow cells, you can change between the actual values we are using when we are sending data. So from the top, we can put in access category, we can put in the length or the number of the number we pick in the contention window, the data rate frame for the data rate for our control frames. We can change the different files for our actual data frame. We can change MCS or a modulation and coding scheme, number of spatial stream, and which guard interval we are using in the data frame. And in the bottom, we select the byte sizes for the different frames in a TXP. And the most important one, and is the one we choose for the AMPDU, is a payload we are sending down to the clients. And the last, and the bottom, we can also select if we will use protection or no protection, or request to send, clear to send in our visualization. When we have done this, we get a table of showing duration for all the small parts, all the legacy preamble, frame body, and so on. And lastly, visualize the duration of each TXP. The 2 first scenarios are for A, N, and AC clients, and the 2 in the bottom are for OFDMA. And this 4 graph is for the same payload sent with different parameters. So we will use the data or output from a calculator to play with in a scenario where an AP sends a 300 byte packet down to some clients in a BSS. This is strictly theoretical, and there is no other traffic in the BSS, so we are not taking care or not thinking of beacons and all the other traffic that usually are in a BSS. It's only us and this traffic. The TXP is set up with the best effort access category. We have a contention window of 8. Control frames are sent at 6 megabit per second, 6 megabit. The data frame is modulated with MC7, one spatial stream, short guard interval, EHT or 802.11ac PHY, and we're using a 20 mega channel. This means we are sending the data, the green part we saw from before, at 72.2 megabit per second. And the AMPDU is 300 bytes. With this setup, the duration of the TXP is approximately 400 microseconds. And if we compare it to the data that is coming into the access point, usually on a 1 gigabit wire, duration into the access point is so small, while Wi-Fi needs 400 microseconds to send the same payload down to the clients. So, as Keith Parson always says, Wi-Fi is extremely inefficient. If we change the speed rate for the AMPDU, we have slightly difference in the duration of the TXP, but the difference is not so big as we might think it should be. Number 2 is when we are using 2 spatial streams, the only difference is the duration for a green field or the period we are sending data. But when we are using 2 spatial streams instead of 1, we have an increase in the blue field because we need an extra long training field in the VHA header. And also 80 megahertz to good spatial stream, duration don't decrease so much. So let's use this data and let the access point send this data down to 2 different clients in a round-robin fashion. First to station A, then to B, and back to A. In this scenario, each station will receive a TXP or receive data each 800 microseconds. And throughput for this connection is down to 3 megabit per second. Even if the speed rate for our data is 72 megabit, the total throughput is down to 3. If we send the same TXP down to 4 different clients, each client will receive an TXP or data every 1600 microseconds. And now the throughput is down to 1.5 megabit. So the throughput is way more lower than the actual data rate for our packets because we have a lot of overhead in our TXP. That is how 802.11 works. But this is legacy network, AN or AC. What if we upgrade our network to Wi-Fi 6 or 802.11ax and use OFDMA? OFDMA can subdivide the channel in smaller chunks called resource units, and could be done frame by frame. In this example, I have stolen from David Coleman at Extreme Networks. The channel is first subdivided in 2, then in 4, then one client gets the full channel. This could change frame by frame. But what does that mean for, okay, this one. And when we are sending data from the AP down to clients, we use a frame format called multi-user PPDU frame format from the A2 to the .11ax draft. It consists of a legacy preamble that every packet have for backward compatibility. Then we have some HA preamble. In this field, we send information on how the channel is subdivided and which client are receiving its data on which resource unit. Then we send some training symbols or long training symbol, yeah. And lastly, the channel is subdivided according to the information in the HA preamble. And in this example, we have subdivided the channel in 4. This means on a 52 tones resource unit. And this is 20 mega channel with the same modulation scheme as we used before. Each station will receive its data with a data rate of approximately 15 megabit per second. And that has some impacts for the TXRP duration. The first one is the VHD TXRP I have shown before at 400 microseconds. If we subdivide the channel in 2, our 20 mega channel 2, and use 106 tones resource unit, the TXRP duration will increase to 450 microseconds. The difference is the request to send because I'm using a new frame type called multi-user request to send. It is something we was described in the draft, but I don't think any vendors have implemented it yet. But I use it in the calculator because I use the draft to make it. And of course, since we are sending the payload or the data in a much lower speed rate, the duration for green field increase. And also the HE header will also increase because we are sending a lot of information on how the channel is subdivided and so on. So if we subdivide the channel in 2, the duration will increase to 450. And if we subdivide the channel in 4, the 20 megahertz channel in 4, I use 52 tones resource unit. The duration for our TXRP will increase to 570 microseconds. And let's use this data and see what's the difference between VHD and OFDMA. Back to our 2 client scenario. With VHD or 11AC, we have a throughput of 3 megabit to each station. If we are sending those packets or frames in an OFDMA frame format, we can send to both stations in parallel. Duration of each TXRP will increase, but now we are able to send TXRP to every station more often. So instead of waiting 800 microseconds, we can send a new TXRP for every 450 microseconds. So we can see the throughput will increase from 3 to 5.4 megabit per second. So for small frame sizes, OFDMA will give a higher throughput. What we have in the trivia question, answer number A. But for small frame sizes, increasing in throughput is maybe not the most interesting thing. And if you're happy with the first scenario and 3 megabit per second, but the problem is that the airtime is 100% utilized. When we are using OFDMA and only send TXRP each 800 microseconds, we gain some free or we save airtime. In this scenario, between each TXRP, we have 350 microseconds with available airtime we can use for other things, or we will lower the airtime utilization on the channel. 350 microseconds is not so much, but let's go for the 4 client scenario. This is the VHT or 11AC scenario. If you are sending those frames in parallel on a OFDMA frame format, instead of waiting 1600 microseconds between sending TXP to each station, we can send a new TXP every 570. And now the throughput is increasing from 1.5 to 4.2 megabit. So we have a dramatic increase in throughput for small frame sizes when we are using OFDMA. But again, are we happy with the first scenario, 1 and 1.5 megabit? We will gain over a millisecond of free airtime between TXP for smaller airtime utilization, and this period can be used for other things. That's why we often say if we can get Wi-Fi 6 clients to use OFDMA and send in parallel, the remaining airtime can be used by legacy clients, and all will get a better experience in the network. Also an 8-client scenario, just to show this very fast. In VHT or 11AC, each station have to wait over 3 milliseconds before you can receive a TXP. If you can send it with OFDMA, and we have over about 2.3 milliseconds with gain or free airtime. So airtime utilization will go dramatically down, and we can send a lot of other traffics. So that's why we call this is one of the reasons the protocol is called high efficiency. We send with shared management overhead and can send to more stations or clients in parallel and gain airtime and a more efficient system. The thing I'm talking about till now is for small frame sizes, 300 byte. What if we use frame aggregation and send bigger byte sizes? In this example, we send a frame AMPD of 20 kilobyte. In VHT, this TXP duration will be 2.58 milliseconds. If we instead use OFDMA and send it on a 106 ton resource unit, the TXP duration will increase to 4.89. If we put this into the same scenarios, we will see for VHT or 11AC, we will have a throughput of 31 megabit per second. If we change it to OFDMA or Wi-Fi 6, it's been a very small increase in throughput from 31 to 32, so it's not much gaining of sending big frame sizes with OFDMA. And we can also get some free airtime if we use the scenario we used before. So OFDMA have some benefits for large frame, but not so big as for small frames. So OFDMA is how its best benefit for small frame sizes. Now I told you about OFDMA and how it benefits a lot of clients, especially when we are sending small frames. But it not seems very difficult to implement it and make it work in today's network. And still, no vendors have shown test results proving OFDMA's benefits. They say that they see improvement, but no vendors have shown any proofs. And for us Wi-Fi professionals who do testing in our lab network, it's very difficult to set up an environment for testing OFDMA is because OFDMA works best in a high density network, and that is very difficult to make in a lab network in an office. And also AP have a lot of difficulties, and it's processor consuming to do the processing to find out if it shall use OFDMA or multi-user transmission or all the legacy single user. First of all, then we have to have traffic to several clients in the transmit queue. They have to consider aggregation. There are big mix of clients in the BSS. Someone are able to do the OFDMA. Legacy client must use OFDMA, OFDM, or single user. And this variable distance between the AP and all the clients. So they have different MCS, we have different spatial stream, different types of traffic, voice with small packet, video are very bursting, browsing traffic now and then, file transfer. It's a big mix of traffic, and for AP it's very difficult to know when to do OFDMA or multi-user transmission or all legacy single-user transmission. And in Wi-Fi, the clients still decide a lot what it should do because they are in charge of their own what they do instead of LTE, where the infrastructure or the transmitter are in charge. And maybe also important, in legacy network it was much more easy because the AP just take the next frame and send it. They don't have to consider multi-user transmission or single user. So it's very difficult to make or let OFDMA work in today's network. I hope it will be better, but it has not been done till now. But the last one, a very important thing about Wi-Fi 6. Many people do Wi-Fi net testing on Wi-Fi 6 network, and they say they experience better performance. And they also say it must be because of the OFDMA. Maybe it's not OFDMA, but something else in the Wi-Fi 6 that is better. Because it's not easy to see whether the network is doing OFDMA or just single user traffic. You either have to do some packet capture or spectrum analysis to select or to see if there are OFDMA traffic. So let us see on a 2 spatial stream device on a 20 MHz channel and look at the difference between VHC and HE, or between AC and AX. And let us assume the AP and the clients are near to each other, so we can use maximum available data rate. First, go into the MCS index table. If we look at the red square, it's a maximum speed on an AC client on 20 MHz channel. As we can see, MCS 9 is not valid. So we have to use MCS 8, and this is 173 megabit per second for the data traffic. The same MCS in Wi-Fi 6 is 206. The data speed for the same MCS is 206.5 megabit per second because we have a more efficient use of the frequency space. We have a different setup of symbol time and guard interval. So only by using difference between MCS 8 in the two files are about 40 megabit per second. And if you are close to the AP and can achieve MCS 11, you can go up to 286 megabit per second on the data frame. So let's put this into my Wi-Fi AirTime calculator and see the difference. 20 mega channel, 2 spatial stream, and a payload of 30 kilobyte. First graph is VHT or 11AC MCS8, and it will have a throughput of 136 megabit. Number 2 is the same frame, and now I have turned off protection or turned off request to send, clear to send, and the throughput increased to 147. But for the same MCS index at Wi-Fi 6 or high efficiency, the throughput goes up to 158, and if you can use MCS 11, you have 202 megabit throughput. So just by changing from AC to AX, the increase in throughput is about 70 megabit for this type of frame. And let's go to the most extreme frame. When we are filling up the transmit TXP window almost to the maximum, we are so in this example, we are sending 100 kilobyte of data. VHT will then have a throughput of 160 megabit per second, while the Wi-Fi 6 device on the same MCS will have a throughput of 189, and if you can do MCS 11, the throughput is 254. So you have almost 50% increase in throughput just by changing from AC to an AX client on a single user transmission. So when people experience better improvement, a better experience on Wi-Fi 6, maybe it's not OFDMA or multi-user MIMO if you think that. Maybe it's just ordinary single user transmission on the new Fi. I think this is the last one. So now I think it's go for Q&A. I hope it's been useful and understandable. And yeah.
All right, thanks, Gjermund. That was really great. And well, we do have a few minutes for questions and answers. So if you've got a question, don't be shy. Drop it in the Q&A panel, and we'll address a few things. We did get a few comments from Keith Parsons. So Keith, thanks for joining us today. He made the comment early on just to say thank you for the shout out and that Wi-Fi is terribly inefficient. And I think especially, you know, that graphic where you compare it to the duration of an Ethernet transmission on the wire really drives that home.
Yeah, it's amazing to draw it down on the paper and compare them. And with the use of the calculator and look at different setups, it's you can learn a lot about Wi-Fi and 802.11.
Yeah, Keith also says, I like that Gjermund stated no vendors have publicly shown their testing of OFDMA.
Yeah, it's kids who are actually fighting this.
Yep. Yeah, we've gotten a lot of marketing so far, but we haven't seen a lot of real technical data yet, have we?
Yeah, it's a guy called Tim Higgins. I've done a lot of testing on consumer grade equipment, and he have not a single test have shown an improvement when using OFDMA over OFDM, single use OFDM.
Right. Yeah, and you know, this brings to mind Peter McKenzie's WLPC talk, where he did an OFDMA test, where he was comparing throughput running, I think it was iPerf testing on several laptops at the same time, all of the devices being 802.11ax, including the AP. And in single user mode, they were getting a little bit better throughput than in multi-user OFDMA with that running. And I think, you know, what your slide there where you talked about how with big frames that are used in throughput tests, any efficiency gain is going to be pretty small. So that probably plays into what Peter found in his testing.
Yeah, I listened to that webinar. And if we are using 3 clients on network, and let's say on 20 mega channel, we have to subdivide it in 3 chunks. 1 big or 106 and 2 52-ton resource unit. And if the AP don't change which client using each resource unit every time, usually one client will get the biggest resource unit and the other 2 will have two small resource units, and we have an unequal speed testing, or the result will be unequal instead of changing the resource allocation frame by frame. And Peter didn't either prove if we are using OFDMA or only single user OFDM. So he thought he did use OFDMA, but he didn't prove it.
Yep, gotcha. Okay, so a question here from Frank, and maybe Kelsey, this will be our last question, but he says, what specific use cases justify the need for 100 kilobyte rather packet sizes that would be commonly used throughout the day by many users? It seems my exposure is purely to smaller packet size use cases. If this discussion isn't framed in terms of use cases, it's largely academic, and I'm not even sure why it's added to the spec other than to create more marketing fluff. Anyway, thanks for the discussion. Thanks, Frank. Any comment there, Gjermund?
Yeah, if you listen to Keith's presentation 2 months ago, he showed that almost 70% of the frames in the Wi-Fi network is under 200-300 bytes. A lot of those packets will never they will never use OFDMA because they are management frame and control frame. But if you can get a lot of them into OFDMA frame format, it will be a big gain in the airtime utilization on the channel.
Yeah, there's an awful lot of. Yeah,
but
go ahead.
it has to be a lot of traffic on the channel. It has to be a high density network, because if we shall do OFDMA, we have to have all the traffic in our transmit buffer before the AP should decide how it should send the traffic down to the client.
Yeah, that's right. And then just a typical Ethernet network, there's so much. There's so many packets that are very, very tiny. ARP traffic, TCP windowing, really, really small packets that are just part of normal network operations, that if we transmit using single user mode, we've got all this major overhead. Even though we can do frame aggregation, we still have a lot of extra overhead that perhaps if we can use OFDMA more often, we can reduce the amount of, or how often we have to add all the extra overhead. So that's the promise, but as you saw, it's yet to really come to fruition. So stay tuned, I guess. All right, Kelsey, I think that about wraps it up.
All right, awesome. I think that's all we have time for today. Thank you, Jim, for assisting with those questions. And thank you, Gjermund, for joining us today all the way from Norway. We were really, really happy to have you on. Got a lot of great feedback with this presentation and a lot of great questions. So thank you to everyone else on the line today for giving us 45 minutes out of your workday to dive into this topic. And we hope to see you next week. So thank you, all of you.
Okay, thank you for bringing me in at the show.
Thanks, Gjermund. It was fun. Thanks, Kelsey.
Thanks, everyone. Have a good day. Bye.